Geometric series. It is very important to understand the effect the value of OR has on the sum of a geometric series. Consider three geometric sequences, A, B, and C, where A has a common ratio of OR is equal to 2, B has a common ratio of OR is equal to 1, and C has a common ratio of OR is equal to a half. So starting with the first term value of 1, we get, so sequence A has a common ratio of 2. Term 1 is 1. 1 multiplied by 2 is 2. Multiplied by 2 is 4. Multiplied by 2 is 8. Multiplied by 2 is 16. Multiplied by 2 is 32. And so on, up as far as term 100, which is a really big number. We don't really care what the number is. I just want you to realize that it's a really big number. Sequence B, we're starting off with 1 again. This time we're multiplying by 1 as a common ratio. 1 times 1 is 1, times 1 is 1, times 1 is 1, and so on. And at term 100, we still just have 1. Then sequence C, the common ratio is a half this time. So the important thing here is that it's less than 1. We don't really care that it's a half, just that it's less than 1. So again, starting at term 1, 1 times a half is a half, times a half is a quarter, times a half is an eighth, and so on. And we end up with a really small number for term 100. Now, if we were to have a look at the series of these sequences. So again, we were going to have the same sequences, A, B, and C. And this time we're going to have a look and see what happens when we add up the terms. So for series 1, so focusing on sequence A, so we have 1. So term 1 is just 1, so S1 is 1. Term 2 is going to be 1 plus 2, which is 3. So S2 is going to be 3. Then S3 will be 7 because 1 plus 2 plus 4 is 7. S4 is 15 because 1 plus 2 plus 4 plus 8 is 15, and so on. And up as far as S100, which is a really big number. For sequence B, again, we have S1 is just 1. Then S2 is 2 because 1 plus 1 makes 2. S3 is 3 because 1 plus 1 plus 1 makes 3. And S4 is 4 because 1 plus 1 plus 1 plus 1 is 4, and so on, up as far as S100, which is 100. Then for sequence C, again, we start off with 1 because term 1 is just 1. So then S2 is going to be 1.5 because 1 plus a half is 1.5. S3 is 1.75 because 1 plus a half plus a quarter is 1.75, and so on. And notice that as our S's increase, so we get S3, S4, S5, S6, notice that our sum is getting closer and closer and closer to 2. 1.96875 is very, very, very close to 2. And S100 rounds off to approximately 2. So it gets closer and closer and closer to 2. It's tending to 2. So we're going to take each of the sequences and we're going to look at them in a bit more detail. So we're going to start off with sequence A. Okay, so the next slide will just contain sequence A. So sequence A, again, is 1, 2, 4, 8, 16, 32. And the series is 1, 3, 7, 15, 31, and 63. So if we were to draw this out on a graph, this is what it would look like. So this is the yellow line. So if OR is greater than 1, in this case OR is 2, but it doesn't matter what OR is so long as it's greater than 1, the values of Tn and Sn, as n gets bigger, they increase very rapidly. We can see that for Tn, the numbers are getting bigger very, very, very quickly. And likewise for Sn, the numbers are getting bigger very, very, very quickly, and they become very big numbers. So drawing this on a graph, so we have S1, 1. So that first red point there is S1, 1. So this is for the Sn. So this is Sn of a geometric series. The graph drawn here is only focusing in on the series, not the actual sequence. So our second red point is S2, 3. S2, 3. So that comes from here, S2, 3. And our third red point is S3, 7. S3, 7. So that's coming from here. So our next point, if we could fit it on the graph, which we can't, would be S4, 15, and then S5, 31, and so on. And you can clearly see that the graph shoots upwards. It gets bigger and bigger and bigger very quickly, and then it shoots upwards. And that's the main thing I want you to take from this, that this is what the graph would look like. If OR is greater than 1, it would shoot upwards. Next, focusing in on sequence B. So sequence B was 1, 1, 1, 1, 1, and the series was 1, 2, 3, 4, 5, and so on. So this is if OR is equal to 1. So it's highlighted in yellow. So we can see it actually just looks like a straight line. So if OR is equal to 1, then the sequence behaves like an arithmetic sequence. Remember, these are geometric sequences where we're multiplying by a common ratio, not adding. So it behaves like an arithmetic sequence with a constant amount added each term. So this is what the graph would look like. It would look like a straight line if the common ratio is equal to 1. So next we're going to have a look at sequence C, where the common ratio was less than 1. And we can see, again, it's highlighted in yellow. So this is what it would look like. And we can see that it shoots up quite quickly, but then it levels off and the red points get closer and closer and closer to 2. So we saw that for series C. So we see that S100 gets closer and closer and closer to 2. It doesn't actually get to 2. It just gets really, really, really close to 2. So if OR is less than 1, in this case, OR is a half. Now, it doesn't matter that it's a half. It could be a quarter, it could be 3/4, it could be a third. It doesn't matter what it is, so long that it's less than 1. It will have the same look on a graph. So then the value of Sn is said to have a limiting value. So Sn, we can see, is getting closer and closer and closer and closer and closer to 2. In series C above, the sum Sn approaches the value of 2. So again, we can see it's getting closer and closer and closer to 2. By taking sufficiently large value of n, we can make Sn as near to 2 as we wish. That is, we can make 2 minus Sn as small as we wish. We say that Sn approaches a limiting value of 2 as n approaches infinity. This is written as Sn approaches 2 as n approaches infinity, or you could say the limit of Sn as n approaches infinity is equal to 2. So the bigger n gets, the closer and closer and closer Sn gets to 2 in this particular series. In words, we say that the limit of the partial sum Sn as n tends to infinity is 2. Now, we suggest that you look back at the video in this playlist of limits of sequences if you're a bit unsure on this, because I went into detail on what limits are in a previous video. It's in this playlist, and we will cover this again in calculus. Now consider the formula for the sum to n terms of a geometric series if OR is less than 1. So Sn is equal to A times 1 minus OR to the power of n divided by 1 minus OR. So this is the formula in our formula book. No need to learn it off. It's important to also note that the little lines either side of the OR, they're known as the modulus. If we are to take a modulus of a value, it has to be a positive value. So this comes up in a few different chapters in maths, but even if that was a negative number, we would take the OR to be positive. Whenever we see these little lines, it represents what's known as the modulus. So just taking the positive value of it. Okay, so go back to this formula now. So when OR is less than 1, OR to the power of n will approximate to 0 for large values of n, i.e. OR to the power of n approaches 0 as n approaches infinity. So the bigger that n gets, the closer OR to the power of n gets to 0. So let's say, for example, OR is equal to a half. It doesn't matter what OR is, so long as it's less than 1. So I'm just going to use a half as an example. Then OR to the power of 1 is a half to the power of 1, which is 0.5. OR squared is a half squared, which is 0.25. OR cubed is a half cubed, 0.125. OR to the power of 4 is a half to the power of 4, which is 0.0625. And OR to the power of 10 is a half to the power of 10, which is 0.000976. So notice that the bigger that the power gets, the closer that this number gets to 0. So we're getting closer and closer and closer to 0. So as n approaches infinity, so the bigger that n gets, the closer OR to the power of n gets to 0. If we take some even bigger values now for the power, OR to the power of 100 is a half to the power of 100, which is 7.8 times 10 to the power of minus 31. So basically a really small number, really, really close to 0. or to the power of 1,000 is a half to the power of 1,000, which actually gives us 0 in the calculator. So the calculator actually just rounds it off because it's so close to 0 that it just rounds it off to 0. But we know that it's not exactly 0. It's just a very small number. And if you wanted to try 10,000 into your calculator as your power, again, the calculator will give you 0 because it's rounding it off to what it's very close to. Thus, Sn is equal to a times 1 minus r to the power of n all over 1 minus r becomes Sn equal to a times 1 minus 0 all over 1 minus r. So r to the power of n just becomes 0. Therefore, Sn is equal to a over 1 minus r as n approaches infinity, because we just lose the 0 basically, and then 1 multiplied by a is just a. Or you could say the limit of Sn as n approaches infinity is equal to a over 1 minus r. So all of this gives us our rule. For a geometric series with r less than 1, the limit of Sn as n approaches infinity is equal to a divided by 1 minus r. So this is given to you in the formula book. You don't need to learn it off, but just to show you where it comes from and why it is true, I just wanted to show you the kind of proof behind it. And just to show you in the formula book, you will see it at the bottom of page 22. So S infinity is equal to a over 1 minus r, given that the modulus of r, so the positive value of r, is less than 1. So example 3, find the sum to infinity of the geometric series 16 plus 12 plus 9 plus ... So I write out my sequence, so 16 plus 12 plus 9 plus ... A is 16, my first term. To get r, I'm going to divide term 2 by term 1. So 12 divided by 16 is 3/4. So we're multiplying by a common ratio of 3/4. From the formula book, I have the limit of Sn as n approaches infinity is equal to a over 1 minus r. I replace a with 16 and I replace r with 3/4. And that gives me 64. So just into the calculator and you get 64. So the sum to infinity of the geometric series 16 plus 12 plus 9 plus ... is equal to 64. So this series is tending to 64. It's getting closer and closer and closer to 64, but it doesn't actually get to 64. So the bigger that n gets, so as n approaches infinity, so the bigger n gets, the closer and closer and closer and closer the sum will get to 64.